This is a paperclip, specifically a jumbo paperclip that I've been using in many of my videos in the past few weeks. Setting this aside, this is a fragment of a smaller paperclip, and this is the other part of the small paperclip that I broke off, and we're gonna get rid of this part of the paperclip, and we'll call this a paperclip nub. Just to give you an idea, this little nub is only around 2.5 centimeters long. Okay, so this is a very small piece of metal. Do you think this little paperclip nub will be able to pick up VHF TV stations, FM radio stations, and NOAA weather stations? All of them operating on the VHF band. Do you think it's possible with something this small? Well, you're gonna find out. All right, for the first test, we're gonna try out this tiny little paperclip nub with FM radio, which operates on the VHF band. So the frequency that I'm choosing is 99.9 megahertz. This is WKIS. This is an FM station that is 20.2 miles away. Let me turn up the volume. I don't have anything plugged into the RTL SDR at the moment. I'm using cubic SDR on my Mac with an RTL SDR in order to tune FM radio. Let's see what happens when I plug in this paperclip into the RTL SDR. Again, this station is 20.2 miles away. This is the FM band, which is the VHF band. Let's see what happens. All right, so as you can see, literally with this paperclip nub, it is coming in. Also, as you can see, there is digital information being sent on either side of the analog FM signal. Will this little paperclip nub be able to receive digital radio broadcasts operating on the VHF band? Well, let's see. All right, I'm gonna type in HDFM 99.9. We'll do subchannel 1. Let's see. Look at that. This antenna does not have a resonant frequency of the VHF band at all. And look at this, it just decoded album artwork. It just got all of this data from this little paperclip nub. How could this be? How could an antenna that's not even VHF pick up a digital radio station? All right, now I'm gonna pull out the paperclip nub just to show you that there's no funny business going on. Oh, look at that, it just stopped. Again, I'm over 20 miles away. I'm 20.2 miles away from the transmitter, and I'm only on the 3rd floor of this building, and the ceiling is made out of concrete. So how could this be? Well, let's check out some other stations. All right, I've brought back up cubic SDR, and I have the RTL SDR plugged into my Mac with the paperclip nub acting as the antenna. And let's go over to the NOAA weather band. So I'll go to 162, let's do 0.55 megahertz. Bring it over to the NOAA weather band. I'll click FM mono, which is what they use. And then let's see here. There seems to be 2 signals that this little paperclip nub is picking up on. So let's see, let's go into 162.55 right here. And let's shrink the bandwidth.
Seas around 2 feet. Intercoastal waters a moderate chop. A slight chance of showers in the morning. The marine forecast for the following marine location is Steam Bay.
Wow, look at that. Static free. Look at how good it sounds. It's static free. This little paperclip nub is getting 162.55 megahertz. This is on the VHF band.
A chance of sprinkles.
Now let's go over to another one. Clean this up a little bit. And there we go. 162.50. This is 162.5 megahertz. with this little thing. How the heck is this possible? How is this little paperclip knob that's only a few centimeters picking up something that should require like this ginormous multi-foot long antenna? How is that even possible? Isn't there just supposed to be static? What's going on? And then, make sure that I'm not, doing any funny business. Let's take out this paperclip knob. And now it's complete static. So let's test out an ATSC 3.0 station operating on 192 to 198 megahertz on the VHF band as well, and I'm going to show you what happens with the paperclip nub plugged in to a network connected tuner called an HD home run. All right, I have the little paperclip nub inserted into the HD home run. As you can see here, I do have the power cord taped down just because it's a little loose, but other than that, it's just your typical standard HD home run, and I'm using this tiny little paperclip nub as the antenna. I have my Windows 11 Parallels desktop running on my Mac so I can bring up the HD home run config GUI. But first, before we get into this, I want to start explaining why you can receive VHF signals with a tiny little antenna like that. So there are three main things that you should know. Number one, how strong is the signal coming in? 2, how much noise is there? These two are combined for signal to noise ratio. That is a crucial measurement. And 3, what modulation is being used? How is the signal actually being modulated? These 3 are the main things that matter. Now, this paperclip receives all radio frequencies. This paperclip nub receives all radio frequencies. This big antenna here receives all radio frequencies. But there is a difference between this and a paperclip. This paperclip is really good at receiving around 1 gigahertz. The standing wave ratio is very low, and the resonance of this paperclip is very high, around 1 gigahertz. And yet this paperclip isn't even really a good antenna at 1 gigahertz, even though this is optimally where it will perform. You could have a big Yagi that had tons of elements and would have way better gain, directional gain, than this omnidirectional paperclip. To say that you need something like this in order to receive VHF frequencies is just plain wrong. Yes, using this will get the signal in way better than something like a paperclip. This will perform way better because this metal is cut to have peak resonance for certain frequencies in the VHF range, which is why it performs the best. That's why we have large antennas. That's why we have antennas that are cut to specific frequencies, because that is where they perform the best. But does it mean that these elements will never receive UHF frequencies or SHF frequencies? No, they will still receive them. They just won't really receive them that well, which means that these would need an aid. These would need higher powered UHF and SHF signals, or modulation that allowed for the reception of the signals with something like this while being very weak. This antenna will perform optimally in the VHF range, but that doesn't mean that something much shorter couldn't also receive the same wavelength that this was receiving. It would just mean that this would receive it worse than something like this would receive. So most people grasp the concept that if the signals are extremely strong, that you will be able to receive something like this that would normally require a much larger element with maybe something like this when the signals are extremely strong. But what a lot of people don't realize, especially those that grew up around the analog era with broadcast, NTSC, analog TV, is that we now have something called digital modulation and something called robust digital transmissions that allow for the reception of signals below the noise floor. Let's say you need these big, long VHF elements to get in a TV station because of the signal and noise, and because of the modulation, that because of these 3, you need this big setup in order to get the TV signal. Well, let's say they tripled their power output, right? All of a sudden, you could probably collapse all of these elements and get them down to this real squatty level, and it would probably still come in the same as it did before with them extended. because now the power level is so much higher. Now, the same sort of thing applies with modulation. If before it required a 15 decibel SNR, and now you can get it at -5 decibels, well, why would you need something like this when all you need is something like this and it can still come in? And RF is RF. Let's say 30 years ago, a station was operating at the same power level as a station now, just for the sake of argument. Let's say this was just plugged into a tuner 30 years ago and it was receiving a station at -5 decibels. Well, back then in the analog era, there was no way for us to use a signal that had an SNR that low. There was no modulation that allowed us to receive TV that low. So you would need a much bigger antenna. Well, now we have modulation that allows us to receive signals at -5 decibels. So what has changed? The radio waves haven't changed. What has changed is the modulation. The difference is this paperclip is probably going to just get it in at 5 decibels below the noise floor, where something like this will probably get it maybe around 40 decibels above the noise floor, because these antenna elements are optimally made for the VHF band. And that is the difference. It's not that a paperclip can't receive VHF, it's that this paperclip can't optimally receive VHF, unlike how with these rabbit ears with their long elements can receive VHF optimally. Every single FM radio station that this antenna is receiving right now, this paperclip in my hand is also receiving. The difference is most FM signals that this is picking up are below the noise floor, and only a few that I could show before were actually above the noise floor with this. But with this, most of the signals are above the noise floor and they're extremely strong. Just because this is receiving them below the noise floor or extremely weak, that does not mean that this is not picking up those frequencies. This means that it's not picking them up as well as this is. By the way, there's no way to receive FM radio stations that are analog below the noise floor. So if you wanted more analog FM radio stations, you would want to use this. I hope that's pretty self-explanatory. So if you were following, there's basically two ways to make a paperclip receive VHF. Either A, the SNR has to be really high, which means either the received signal is extremely high, or the signal is sent with modulation that is incredibly robust, that allows for incredibly robust reception. All right, now that that's out of the way, let's see how well this little paperclip nub can get 192 to 198 megahertz. Let's go to tuner 0. As you can see, I already have it up here. It is currently getting it in at around, it's right around 13 decibels right now. As you can see, believe it or not, this station requires about 13.5 decibels to 14 decibels to lock. It's fluctuating a little bit right now, but this particular modulation that they are using, non-uniform QAM 256 with a 715 code rate, requires that minimum SNR. Now, a few things. We're able to receive this information on the bottom. Why are we able to receive this? Because this data right here where it says PLPs is contained in the preamble of the ATSC 3.0 station, and this data is receivable at almost -8 decibels. So we are around 12 decibels above the noise floor, which means that we have another 20 decibels to go before this data goes away. And then on top of that, the ATSC 3.0 bootstrap is available until almost -10 decibels. So 10 decibels below the noise floor, which means that we're almost 22 decibels away. And a decibel is a lot of power, so 22 decibels is a ton of power that we'd have to decrease. And let me show you, again, it is with this tiny little paperclip nub. And again, I am 17, 18 miles away from this transmitter right now, and I'm able to get this VHF channel with a paperclip nub coming in right around the minimum to receive this station. If I switch it out with this jumbo paperclip, it'll come in. And if they were using something like QPSK or non-uniform QAM 16, we'd be able to watch TV right now, even with this little paperclip nub. But because they're using this particular modulation that again requires that higher minimum SNR, we're unable to watch anything off of this station But again, any ATSC 3.0 station does not matter what it is. It'll always have this L1 signaling information from the preamble available at almost -8 decibels. So let's go through all the other stations that I'm getting in the UHF band, and the results may surprise you. So let's start off with 22 here. As you can see, we're getting in an ATSC 1.0 station WFOR at 18 decibels. It is coming in perfectly fine. As you can see, symbol quality is 100%. Again, just with this little nub. Let's keep going up the dial here. We're getting WLTV on RF channel 23. We're getting WAMI on RF channel 24. Okay, nothing on RF channel 25. Nothing on RF channel, a little bit of something on RF channel 26. Yeah, we're getting WLRN on RF channel 26. We're getting WSFL on RF channel 27. We're getting TBN on RF channel 28. This station is 20.2 miles away. It's fluctuating a little bit, mainly because ATSC 1.0 is so bad with multipath, and especially when you have a smaller antenna like this, it's horrible. Let's keep going up. RF channel 29, as you can see, we're just barely kind of getting in right now. RF channel 30, this is WSCV. We're getting this station in. Definitely this is a telltale sign of multipath, that it's like going in and out like this. So there's a lot of multipath issues, but as you can see, it's coming in. ATSC 3.0 wouldn't have a problem at all with this. RF channel 31, as you can see, this is probably the most stable UHF channel there is. This is coming in at 22 decibels right now. And as you can see, there's no fluctuations at all. The symbol quality is staying consistent. The signal quality is staying consistent. So this works really, really well. Again, this is ATSC 3.0. So all of these stations I'm receiving right now with this little paperclip nub, and I did a scan, and I was able to get in 27 channels with this little nub, with the closest station about 17 miles away and the furthest station over 20 miles away. And again, this is because all of my signals here where I am in Miami, Florida are extremely strong. Look at how many are in the -20 dBm range. And WPLG here is showing up as -25.36 decibel milliwatts for a signal power. That is extremely strong. So first off, it doesn't matter how far away you are. That is the biggest misconception. I could be 1 mile away, I could be 30 miles away. This matters. Whatever this is what matters. This is my results list for where I am in Western New York. And as you can see, I only have 2 stations that are coming in that -20s range. And believe it or not, in the video that I made like over 3 years ago, I was actually able to get WUTV, WNED, and WPXJ coming in with a paperclip. And as you can see, it ranges from like -23 decibel milliwatts all the way to like -31. Now, the easiest station to receive is actually none of these at the top. It's all the way here, WNYO. This is the ATSC 3.0 station in Western New York. It is 16.7 miles away. It's coming in actually not as good as the ATSC 3.0 station is in Miami. This is closer in Western New York, and it's actually at a way lower power level in comparison. But this station is coming in at -33.35 decibel milliwatts according to the Rabbit Ears study. That station is extremely easy to receive because that lowest PLP on WNYO only requires a 9 decibel SNR now. So I can walk around with a paperclip attached to a tuner. I can walk up and down the house. I can walk outside, inside, in the basement, and it's still able to lock on to that PLP 0. I have unplugged that little paperclip nub, and as you can see, WTVJ, it's fluctuating a little bit, but WTVJ is still barely coming in right around the noise floor. So the reason why it's fluctuating like this is actually because of a glitch with the HD home run. So technically right now it should just be just slightly below the noise floor because it was going on and off from 0 and then below 0. But the HD home runs Sony demodulator chip inside is unable to display information about the signal below 0 decibels. And this is a known issue. In fact, Silicon Dust told me that if you are watching a TV signal that is capable of being decoded below the noise floor, it'll still work. It just won't display any information about it. So as you can see, it's going from 0 decibels right now to below 0 decibels, and it's still saying 0, and then it just gets rid of everything, but technically it shouldn't be doing that. This is a glitch. The ATSC box does not do this. It does show below the noise floor, and you can actually watch it go down as you attenuate the signal more, which is pretty cool. Next, I decided to use my phone's metal chassis as an antenna. Now, a lot of the antennas are actually internal. Some phones do use the metal chassis, if they have one, as the antenna, but as you can see, there's these little plastic bits here. That's where a lot of the Bluetooth and Wi-Fi signals pass from an internal antenna. But I decided to use the metal chassis to see how well a metal chassis of a phone could pick up TV signals. Just a quick warning beforehand, it's a very crude example of this, but it gets the job done, it gets the point across. This is touching the exterior of my phone, the metal chassis, and as you can see, let me bring it in and show you. So it is touching, as you can see here. Now, if we look at HD Home Run Config GUI, as you can see, symbol quality, 100%, signal quality, we're at around 15 decibels right now, signal strength around -62 decibel milliwatts. Let's watch TV using this phone's antenna. So let's watch an ATSC 3.0 channel. Let's do this TV. Wow, look at that. This station is operating on the VHF band, right? VHF band, this station is almost 20 miles away, and yet look at this. This tiny little piece of wire touching my phone. So let's do an ATSC 1.0 station. Let's do WSCV. Look what it's coming in at. Around 30 decibels right now with this phone. And just to show you that this works, let's let me bring up WTVJ.
But once again, at 4:12 in the afternoon on this Friday evening, you can imagine traffic is... Which is why the federal
government... So let me bring my phone away.
More still has to be done.
Whoa, what happened? So what happened is it went from a nice and clean, stable signal with the signal coming in at over 28 decibels while using the metal chassis of the phone. And as soon as the phone got put away, it went back to having that multipath, sporadic, coming in and out at different levels. That was the case before when we were just using this little paperclip nub. The takeaway from this video should be that we don't need optimal antennas in order to receive certain frequencies. We can use something like this and it'll still work if the signals are strong enough or if the signals are robust enough. The best thing would be to have the signals extremely strong and extremely robust, and you can do that with single frequency networks and low modulation encode rates like QPSK 215, for example. So if you combine a single frequency network with low code rates and very simplistic modulation, you would have portable devices like this take advantage of low VHF frequencies. So if you didn't know, the more robust you make a signal, the more error correction you're adding to the signal, which means there'll be even less data that you can put on that 6 megahertz RF channel. Now the good thing is coding has gone a long way. You could have an HD MPEG-2 video stream taking up 8 to 10 megabits per second, but the VVC equivalent would only take up 1 megabit per second. So as long as you use efficient coding, there's no waste being involved by making the signal more robust. You can just use more efficient coding. Additionally, broadcasters don't just have to waste their entire 6 megahertz band with a low code rate QPSK transmission, because what they can do is they can allocate some time resources or some frequency resources to that Or even better, they can use layered division multiplexing, and they can have one PLP as QPSK. It'll just slightly raise the required SNR just slightly. And then they can have a whole nother 6 megahertz band with a fresh start that they can do a normal transmission that requires more so of a normal like 15 decibel or so SNR. So that's one of the amazing things about ATSC 3.0 is there's so much flexibility. There's so much potential to do amazing things like this. I go into detail a lot more in the video that is linked right up here, and you can go check that out if you want. If this paperclip could receive VHF, then do you think this Wi-Fi antenna could receive VHF? Because this is where the antenna is. It could totally receive VHF if the signals are robust enough or strong enough. And I'm being overly conservative with the gain on this device. And that's assuming that a manufacturer repurposes this antenna, which I highly doubt they would do if they were to start using broadcasts in the 470 to 608 megahertz range or even below that into the VHF range. The 3GPP just announced a few months back that band 108, which is from 470 megahertz to 608 megahertz, is considered a broadcast band for use in broadcasting, with the intention to bring that capability to existing devices like tablets and smartphones that rely on cellular infrastructure. So there is already a push to add 470 to 608 megahertz for broadcast on mobile devices like these from the 3GPP. Major manufacturers of chips like Qualcomm are on board to do that. So there's definitely a lot of momentum. Also, if you're interested, check out my interview with XGen. XGen proved that you could easily have 5G broadcast on mobile devices as well. Thank you to all of those that have made it to the end of this video. Patreon members and channel members, I appreciate your support. If you want to become a channel member or Patreon member, if you think this stuff is cool, I'll leave a link in the description below. Other than that, thank you so much for watching this long video, and I'll see you in the next one. If you like this video, consider subscribing and liking the video. Follow Western New York Over the Air on Instagram, Twitter, and Threads at WNY Over the Air. Like Western New York Over the Air on Facebook at facebook.com/WNY Over the Air. Support the channel on Patreon at patreon.com/WNY Over the Air. And check out WNYOvertheair.com for live band scans, cord cutting tips, and much more.
Southeast Florida and originating from the National Weather Service Forecast Office located on the main campus of Florida International University. Now for the